Hi everyone, welcome to MathSpellBook. I'm your host Peter, and basically we are going to get back into arc lengths today. Maybe we'll probably go into like more other subjects, like maybe we'll probably cover some physics as well, because I feel like I haven't covered that much physics. Actually, like maybe we'll like do a little bit of physics, a little bit. So let me just open this book. This book is called Thinking Physics by Epstein. I think it's a really popular book. Let me just reduce the size. Oh, that's too big. Yeah, there we go. I think this will be the proper size. Maybe we can make it a little bit bigger. There we go. I've been doing like a problem out of this book for, like, actually this morning I just did this problem. This problem was actually pretty challenging because I had to think about it for a second. I had to think about it for a while, and I was like, wait, I'm not getting any of the choices here. So I had to do some like mathematical maneuvering. So what do we got here? Not far. Look at the speed graph and tell how far away from the starting point this thing ended up. So let's see what we got. It is impossible to tell because the graph is not on the numeral scale, and it's ended up at the starting point. It did not end up at the starting point, but where it ended up can't be told. Okay. So basically, what's the question here? The question is, look at the speed graph and tell how far away this from the starting point this thing is. Okay. So let's see. Well, it did travel some distance here. Like probably like let's basically assume that basically it's 5. So let's say it traveled like at least 5, like as a staple marker. We're not saying it's exactly 5, but I guess like if we imagine numbers here, we'll make it much easier. And if this is speed and this is time, so it went 5, let's say meters per second. Let's just put it that way. 5 meters per second, and then at this point we'll say it went 10 meters per second. This point, so let's say this is from 1 second to 2 seconds, and then 2 seconds to 3 seconds, and then we'll say 3 seconds to 4 seconds here. So at 3, I would have to say and it went 30 seconds, like 30 meters per no, not 30, what am I talking about, 15 meters per second with this. So in total, we would have to say that it went 5, and then I would have to say, based on this graph, it looks like it went back to its starting point. Because these are like, so if we assume that these are the same units of speed, and obviously with speed times distance, we are basically given the distance. Given the amount of squares we have here, I would have to say that it goes back to its starting point. It ended up at its starting point. It did not end up at this. Yeah, it looks like it ends up in the starting point. So tell how far away from the starting point. I think it's back at its starting point here. I don't know if we can flip this around because the answer is right here. View. Can we rotate this? So rotate to the right, and we'll move it again. So rotate it to the right again. Okay. So here we go. Oh, this is multiple choice. I didn't realize that. Oh, okay. So I have to flip this back around to see what it said originally. I forgot all these questions were multiple choice. I thought those were parts of the question. Rotate it back around. It ends up as a starting point. Yeah, that's what we said before. So let's just find out why we were correct in that case. Because even though my answer is correct, I just want to understand why it's correct, so that way, like, you know, get a better visual reason why. What does it mean when the speed is less than 0? It means that the thing is going backwards. Yeah. So whenever it goes like in the opposite direction, that means it's like reducing speed. Or it's going the speed in the opposite direction. So basically it's telling you how the graph should be viewed as. Units don't matter if you compare things with similar things. Okay. That was actually a pretty good problem. It didn't put you in the world of numbers, it actually just made you think about how to think about the physical system, which I think is pretty good. So we'll just rotate this back. There we go. Alright, so that's our little physics question. What's the next one? So I'll probably save this for whenever we want to get back into it. Anyway, let's check out what we got to do here. So the last time we actually did this problem, which was a pretty difficult problem actually. So why don't we do 24? 24 looks like it's going to be a pretty interesting one. It looks challenging, but let's do it anyway. Oops. Expand that, move it right here. Like I say, we're dealing with arc length, so according to this, we need the formula of x prime, or in this case it's y, so we'll just say g y prime. So now we have, so x is equal to y. Alright, so now we have to take sure that we differentiated that right. And our a is 0, and our b is the natural log of 2 over the square root of 2. Okay, now is the tough part, putting all these things together. So, square root of 2, then 1 plus, oh, I think we also have to have a square root here, right? I mean, not a square, but just a square variable. Yeah, I think we need a square variable here. Okay, so this one's going to be challenging, so I'll just say that. So we won't write anything for this part yet, so we'll just do it outside of it, so that way we can write it at the end. Like this. Well, this is going to be fun. Well, that doesn't look like a 2, that looks like a V. Or a menu. Okay, so rewriting this as let's do it like this. This. So these two, it will be 4 times 2. Then it'll be 2. And then the next one. So this one, it would be 2 times 4. Yeah, now it would be 4. And then that would be over 16. And that'll be as 1, so we can reduce that to 4, and the next one it will be the same thing. Yeah, the next one will be the same thing, so it will be over 4, and that will be plus 4 over. Now I gotta do 16 times 16. Luckily I have my calculator with me. Okay, so let's reduce this. So we have 1 over 64. And that plus, and then this will be a half. And then, yeah, that'll be minus a half. And then we're left with 8. Okay. put that into our formula. So 1 plus 8. Okay, now I think we can make this a little bit, well, I think we can combine like terms here, so we'll have a half here plus 8 and I think we are familiar with this because it does look familiar. We can reduce this to because what we originally started with was, where is it? There it is. So because this one was hold on. Oh yeah, because we put the minus because there was a negative sign here. Okay, so that is correct. Okay. So to make sure that that is correct. So I want to make sure that the notation is correct here. Yeah, I think that is correct. It's just that this one is actually the, I guess the addition version of this, just to be perfectly sure. So now we are left with this by y. So now we can actually separate it like we did last time. So 2 square root, which is e square root of 2 here. Y. And this one we can reduce it here. that will become negative square root of 2, and then basically we'll have it like that. Let's bring this up here. Just a 2, and then minus 116 minus 2. Hey Sasha, and hey there, Mean Machine Rex. How are you guys doing today? Okay, so minus 1, that all multiplied by 2, 116, minus 1. Okay, so this crosses out, and the natural log of 2 minus multiplied by 2, and then that crosses out, and we're left by negative, so the natural log of negative 2. This math looks so hardcore. Not really. It's just that there's a lot of terms involved. Like the problem we have is this. It's just mainly a lot more steps involved. Oh, you know what? My thinking is not correct here, because if we have a negative 1 here, then that would be a negative. So technically, if we think about it, it would be 2 to the negative 1, which means it's a half. If I'm wrong, please correct me, guys, because I feel like that's usually how it is, because I think when it's a number in front of the natural log, it's usually considered as an exponent of the number within the log, natural log. This is where, like, I have to remember my basic algebra now, because I'm like, is that how it works? I hope so. So this will be 1, which is 1 times 2, and then 16 here. Minus 1, so that would just be negative 1. I mean negative a half, sorry. Negative a half. So we're left with 2, and then make that positive. So 32. And now we have to do the hard part, which is 64, 32 plus 32, 1 over 32, and 65 over 32. I think that is correct. Let's take a brief look at what, because when we did this step, like this is a negative, and I want to make sure that that's proper. Yeah, so because like negative, I'm sorry, if you basically take the derivative of this, it's basically negative. Yeah. Okay, that looks like it works. Yeah, and then we rewrote it like this because obviously it's the negative sign over here. And then we just did the arithmetic here. Well, the algebra actually. We did the algebra here, and we came up with this. And then what we have, we get 1, which gives us back the addition version of what we started with, which is like this, and then basically we just rewrote it like this, and then we just took it apart like we did the last time. Well, like last stream we did. Then we do it like this, and I do believe, yeah, because then we would basically do U substitution here. Like, I know when you do U substitution, you're supposed to change these, but we're gonna revert them back anyway. So I'm like, actually, when I was taking calculus, I never changed these. I probably should, but I never ended up doing it because I'm like, I'm going back to Y anyway. So it's like, I don't know if that's proper for like doing for the maths, because for me, I never change them because I'm like, I'm going back to the original variable anyway. But, you know, like, for all those that are more experienced in math than me, please, like, let me know, let me know when I actually have to change the variables. Like, I mean, not the variables, but the parameters here. Because, like, whenever I did problems like this, I never changed them because I knew I would go back to the original variable that we started with. But, you guys let me know when I have to actually implement changing this to the, I guess, the U version of the particular parameters here. Maybe in like harder problems we have to convert it. Yeah, that looks right. That looks right. Lucky I caught on with this negative sign here, because that probably wouldn't have been good. So this problem is, I think, number 28, right? No, 24. 24. So 24, and I think it's 6.5, so... calculus for... number 24. Show all the steps here. Okay, so it is the problem we started with, okay. Yep, we got it. Awesome. We got that problem correct. Okay. I think it was because of the example like the example in the beginning of the chapter that I recognized this, and I'm like, oh, I mean, it wasn't the exact same problem, but the layout is the same. Like, basically it makes you think that you're doing you have to do like this type of sequence, well, not sequence, but this type of layering, I should say. And then like you have to recognize this, and I'm like, oh, okay, I recognize this pattern. We're working with like arc length, but welcome to the stream, Anji soon. I'm sorry if I mispronounced your name. Is it okay if I call you Anji? If it's all right with you, like, let me know how you want me to pronounce your name. I want to make sure that I address you in the way that you want to be addressed. But welcome to the YouTube live stream. We're working with arc length. I just wanted to try out this problem actually. I really want to try these problems, the ones with the pictures, but I don't have any experience with hyperbolic functions. I don't know, guys. Maybe we should take a detour and learn some hyperbolic functions. What do you think? Because I mean, we're still on arc length, and I think it would be pretty cool to actually like learn more about that. Actually, I probably should get into hyperbolic functions. Actually, is there a chapter on them in this book? Trigonometric functions and their inverses. Do they have hyperbolic functions, or do I have to go to a pre-calc book to learn this? No, they're not here. Yeah, man, it's okay. My name is hard to pronounce for it's okay. It's okay. Actually, like, because of my streams, I think a lot of people from India, like, I think, like, I've met some people from India because of my streams, because I didn't know, like, a lot of people from India like math. But I'm not really a math teacher, though. I basically do math as a hobby. That's just like, I guess, a forewarning I give to everyone that comes to the stream, because it's like, I know people go into math channels and they expect someone to be an expert at it, and I'm like, no, I'm not. I just basically love math as a hobby, as well as physics. Do they even have hyperbolic functions in this book? Let's take a look. This is H. Okay, so hyperbolic functions, hyperloids, hyperbolic sine, hyperbolic functions. Okay, from 400, and so if we go in here, this page is 300. So great, I forgot the page number now. But how's your day going so far, Anji? Hopefully your day is going pretty well. I always want to make sure that you guys are going through like a decent day. Okay, 481. So this one's 480. Exponential functions. 32. So is it? Oh, here it is. Hyperbolic functions. Here we go. That's weird. Why would they put it at the end here? Unless you don't need to know hyperbolic functions for the problems that are in this one. Unless it's supposed to be a review chapter. Let's actually give it a try then, if that's the case. So, because I usually like word problems sometimes because it allows me to apply stuff. Oh wait, hold on. Am I in the right section? Because we were doing arc lengths. Length of a curve. Surface area. And this is 6. Yeah, it's supposed to be like the curve here. So, okay, yeah, we are in length, okay. Okay, here we go. Zoom in here. So, let's do this first one. Oh, don't tell me I need a calculator for these. Oh, it looks like it says, because like the T, I recognize the T because it says you need like a technological application for it. Let's see what it reads. Let's see, the profile of the cable on the suspension bridge may be modeled by a parabola. The central span of the Golden Gate Bridge, see in the figure, is 1,280 meters long and 152 meters high. The parabola is, oh, okay, is a good fit to the shape of the cable, whereas the absolute value of x is less than 604, less than or equal to 640, and the x and y are measured in meters. Approximate the length of the cable that's stretched between the tops of the 2 towers. Let's take this here. We'll copy it. Then we'll paste it down here. Let's move this over here. Make it a little bit bigger for you guys. Okay, so let's take a look. Actually, the picture really does help, though. So the parabola's formula is y is equal to... That's a very, very nimble scalar, actually. I mean, I'm talking about this number here. Because I'm like, wow, that's so precise. But then again, a bridge has to be precise. Here's a good fit. So, we have to approximate the length of the cables that stretch between the tops of the two towers. Okay. So if this is arc length involved, so let's just write the formula for arc length. So that way we know what we're working with here. So this one is in y, right? So we have to do it by x. So this is f of x. Okay. So the absolute value of x is either like the highest it could be is 640. So if we differentiate it, so y prime would have to be 2 times x. And I guess I'll use my calculator to give us the actual number here. Because the way the number looks, it's like 7.4 times 10 to the negative 4 x. And we'll leave it in scientific notation, why not? Okay, so now we have to differentiate this thing. I mean, like put in the formula, I should say. That's going to be interesting. So let's actually figure out what our y and what our b and a are actually before we do that. So we got y here, which is the height, but we also have a Now the question is that do I have to do the arc length on both ends? Like, do I have to do it from the y and do it for the x? Because they give us 2 parameters here. Because this would probably be from 0 to 152. So does that mean we have to change also this formula to a y version of it? Maybe. Because I get a feeling that's where it's leading us to. Because let's see, the original question is approximate the length of the cable that stretches between the top of the 2 towers. So now I have to think about like how. Oh wait, hold on. I forgot something in the formula. Because we have to take into account this one too, so I'm thinking we might have to do that. Because we also have to take into account the height of the... Because if you just have it from here, you're only given the length of this axis, but you also need the length of this axis. So does that mean we have to put the lengths together in some way? Or maybe I'm just thinking too much. So we'll just work with x for now, and then we'll probably do it for y, so that way we can like work our way through it. So A and B for the Y, it'd be from 0 to 52 meters. And then this one is... Now the thing of it is that these formulas have to work together to give us an accurate length for the but then again, I mean, I'm trying to think of it like a vector, because like that way the y and the x don't interfere with each other in some way. Because actually I think this one would probably be harder to solve. This one looks like it could be a little bit easier to solve. Because then we're given, and then, but then we still have the square root here. Because we have to write it like AB square root of 1 plus g of y, g prime of y. I mean, this would get rid of that square root, and then we would be with this square root here. And I think we would have to like write this on this side and put plus y. I guess this is why they probably make it a calculator problem, because doing it like by hand seems like it's going to be a little bit of a challenge. I'll be right back, guys. I just got to refill my water. So, BRB. Alright guys, I'm back. Sorry to keep you guys waiting. Yeah, that's the thing I don't like when it comes to like technology-based problems, because it's like everything has to be done on the calculator. Let's see, here we go. And x and y are measured in meters, okay. Now the parabola gives a good fit to this shape. So, where the absolute value of x is... So in that case, maybe we have to do it by x because they give you the value of the absolute value of x. So maybe we have to do it this way. Let's give that a try. Maybe that will. It might not help, but it might make it a little bit easier to visualize or to like kind of like think about. According to this, it's 5, 6 times 10. Yeah, it's all under the square root. So there's no way to like reduce this even more. I guess we can't do this one because like I guess like you can't do this without a calculator at this point. Or I mean like any technological means. Usually I like dealing with problems that I could just like work with, like just work with by hand. Oh well. So since we do have a little bit of, I think since we did dig deep into understanding a little bit of arc length, maybe we'll understand where is it? Line integrals. So I guess right here. Line curves in space. Length of curves. Here we go. Okay, so they familiarized us with arc length. Suppose a parameterized curve. And we were given this last time, so we have to take the derivative of everything within that. So let's see if we can answer some questions in part 1. Arc length calculations. So arc length approximation. So is this more on arc length? Find the length of the two-dimensional curves. Okay, so let's try it, shall we? So let's copy, paste. Expand this here. Okay, so we got x and y, so I think we have to take the derivative of both of them. So this one would be 6t 16 only. Then this one would be 8t, and okay, so now we got to do the formula. So 1, we take the square root of I think it's by t. I think we do have the formulas here, just in case if we forgot. So this is the arc length. See, for the book, first part, I think it was here somewhere. Arc length of a function. Yep, I think that's the definition we are going with, so alright, so now we have 36t squared plus 64 t squared. And of course we can basically take out like a lot of stuff in here, so we can take the t squares out. Let's see, 64 and 36. We know we have a lot of common factors with these two, but I don't want to go with 2. Because 6, and then we have 8 here. I think we can go with 4 with this, right? So let me check here. Yeah, we can go with 4. So let's go with 4 squared. And then we're left with 6. Oh no, what am I doing? Supposed to be 9. 9 plus 16. And that looks pretty nice. So rise it up a little bit. So now we have 2 and times 5, because that would be 25. I will just type in my calculator just to make sure. Yeah, that's 25. So at this point, we're left with 10t, and doing so, we're left with t, and then that's 5t, and then 1, and then we're left with 5. That looks about right. I want to make sure that I did everything right here. So the derivative. Okay, yeah, that looks about right. Let me look at the definition one more time, because I think they want you to take the derivative by t, so I want to make sure that I'm not mixing my variables up. Okay, so I think we can go back. We are on chapter 12.8. The number we're working with is number 9. 8, number 9. Yeah, I think that's the answer. Yep, 5 is the answer. Okay, cool. We're going through the basics. Okay. So I think we'll jump around. So I think 15 could be a good one. We'll work our way up and then we'll go into much harder functions. Because this one, it kind of looks simple, but at the same time I don't want to overestimate it. Or underestimate, I should say. So, this one, so R, T, so this is 3, and then -4, and then 3, so we're just left with a vector, literally. And, oh, come to think of it, I didn't mess up, did I? Like remembering the formula? No, okay. I thought I put a 1 there, and I'm like, wait, hold on. Like, there's no 1 in this version. So from 6 to then 2 square. Okay, so then we're left with, so we have 9, 16, and 9 again. So 25 plus 9. So 25 plus 9, that's 34. And I mean, technically, I don't think you can reduce that. So we're left with 34 dt, which will make it 34 times t. And then we're left with this. So I'll just do all the arithmetic in my calculator so we don't have to worry about anything else. So according to this, it's 29.2. We'll just write it that way. Let me check to make sure that everything's correct. Yeah, because we just have like, yeah. Okay, that looks like it's fine. Yeah, we took the right numbers. Yeah, 34, square root of 34t. Alright, so let's check. This one's 15, so. Exercise 15. Oh, we could have done the algebra approach. But yeah, I think it's still the same though, because it's like basically 6 times and then minus, well, yeah, the 5, yeah. I mean, that's pretty much the same, I think. So 5 times 34. Yep, it's about the same. So we got that right. That's good. Okay, now we can challenge ourselves by doing, I think, problems involving sine and cosine. I think that's going to be more of the challenge. So let's do one that is, let's do number 11, and then we'll work our way up to, I think, number 13. And we'll expand this, drag this here. All right, so for this one, we have, so we take the derivative of that, be negative sine, and this one, it would just be cosine of t, and then this approach, oops, do pi of 0, then we take the square root of sine. Oh, this is going to be like a 1 scenario. Yeah, because then we're going to end up with 9 sine t, and then 9 cosine, and then those will turn into 1. Basically, we're left with 3 in here because these will turn into 1, and we take 9 out, and then basically that will turn into 3, and then we are left with 3t pi 0, which leaves us with 3 pi. That one was problem 11, so yep, 3 pi. Okay, that one wasn't too hard. Now let's move on to, let's try 13. 13 looks like it's going to be an interesting one too, so let me drag this down here, paste, and then we'll expand. Okay, so now let's see, RT prime. Okay, so the first for x, we have negative sine plus, and I think we got to do the product rule. Oh, this is both this is y and x. Okay, I thought it was like I thought it was 3 variables. So we have sine plus sine t plus t cosine t, and then we have this one, we have just cosine t minus cosine t plus, actually it should be another minus well, actually this, yeah, because then this would be like that, and then we'll have cosine, yeah, like t, and then negative sine t. But then if we rewrite it to make sure that everything's distributed, sine plus cosine t and cosine t minus cosine t plus. Okay. That was promising. Now on to the cross out stuff. I didn't realize that. Oops. So sine and negative sine, we're left with cosine t cosine, and yeah, we actually can cross out stuff. I was about to trick myself. Okay, that makes it way easier. So t cosine t plus t squared sine t. Oh, it's another one of these. we all know what's gonna happen. And if you don't, let me know in the chat so I can explain it. Yeah, so we're gonna end up with this. Cosine squared sine squared t. And then that will end up with just t, which leaves us with t squared over 2. Which leaves us with over 2, which is double checking because I'm just making sure that we didn't miss anything. Alright, so this is number 13. So 13. Yep, that's what we get. Cool, we're making good progress here. Let's check out 22. Because 22 is the last one of this part, so let's see if it gives us a little bit of a challenge here. Okay, so t. So that's going to be negative sine of t. Another negative sine of t. And this one is going to be 5 cosine. And then, oops. From 2 pi to 0. So we're left with plus cosine squared plus so at this point we have sine 16 sine squared and 25 cosine t squared. Okay, so we can combine 2 of these. Let me just double check here. So I don't think we can do our typical trick of like using the trig identities this time. Or can we? Let's see here. Because none of these, because the thing is that none of these have any numbers in common. Unless we have to do something ugly, which is like basically like try to reduce them by using like fractions. But oh yeah, we can reduce some of it though. I just realized we have 2 terms that are like terms. So So it will be 25. Oh, here we go. Yeah. See, sometimes taking a second look always helps. Okay, so now we have like terms, so we can take 25 out, and then obviously we're gonna have the trig identities, the sine and sine, which in turn will give us 5. Yeah, that's 1, so it's 5. So it's 5t from 2 pi to 0, which will give us just 10 pi. So this one is 22. Exercise 22. There we go. Cool. So that one was pretty easy. So luckily we saw like the stuff that could have tricked me up actually, because I was like, oh wait, I could do this and I could do that. I have to work on my awareness here. Let's see, speed and arc length. For the following trajectories, find the speed associated with the trajectories. And then find the length of the trajectories of the given interval. I think it's basically asking us to do the same thing we've been doing the whole time. What is the next section actually? Arc length and polar curves. Find the length of the following polar curves. Arc length approximation, use your calculator. No, I usually avoid these questions. Even though I like my calculator, I don't like doing like estimates with it. Usually for me, I just like writing everything out. But at the same time, like if it's something involving like I have to have help with technology, sometimes I'm like, oh, that takes the fun out of it. So, arc length polar curves. The complete circle of R equals... So now we have to do it with polar coordinates. Let's take a look at it. Here we go. The arc length as a function of the parameter. Here we go. Arc length of polar curves. So it has to be a function of theta. So let's just take this, paste it here, so that way we can keep it in mind. So let's see, if f is a continuous and an interval of the arc length of a polar curve, r is equal to f of theta. So where a is greater than 0. So we have to take the original function and differentiate it. So, okay, so r is equal to f of theta, which in turn is a sine theta. So f prime of theta should be cosine of theta. So then we're just going to end up with the arc length of... Are we given intervals? A is greater than 0. So I'm guessing it's supposed to be 0 to A. I guess we can think of it that way, I suppose. So sine theta squared plus a cosine theta squared. We already know where this is going. Then this is all on theta. So this is going to be A, and then it's going to be A theta. Oh no, it's supposed to be a circle, so I'm thinking it's supposed to be from 0 to 2 pi. Because like 2 pi. And the radius is a sine, so basically I'm thinking it's just basically the a is the length of the radius. So technically it's practically pi 2 pi r for the circumference. Let's see if we were correct on that. So this is number 31. 31. Yep, 2 pi a. Okay. Now, these problems probably might be something that I can use. So now complete cardioid. Cardioid. Really hard to pronounce that one. Now I know this has to do with like the curves, like was it parametric curves? I think. Now I forgot the actual equation for a cardioid. I did study parametric curves, but I didn't really go in depth in them. Like I forgot the actual equations for like the heart and the cardioid. Let's write down what we do know. Maybe we'll start there and we'll try to work our way through. Because I think what the shapes tell you is the parameters they go by. Because I think with the circle it was a little bit easier because remember like radius, and also as well as radians. That's how I came up with 2 pi for the top parameter. So let's just like differentiate this so we can get some clarity here. So this will turn into cosine theta. The only thing is that what are the parameters? That's the one thing we don't know. Plus negative theta. So I think we'll just do the FOIL technique outside of the square root so we don't have to worry about mixing up things. So this will be 4, and then -4 times sine theta. Then we're going to get another one, so it's -4 sine theta. And then we're going to get plus 4 sine theta squared. So 4 minus 8 sine theta plus 4. Okay. And that's all going to be underneath here. Plus 4 cosine theta. Okay, so we have some things that can cancel out, or factored out, I should say. So in this one, we can factor out a 4. And this one, we can factor out 4. And this will turn into 1 because of the relationship they have, so we'll have that. And actually, maybe we don't have to do that. Maybe that will be, because I think I see something that looks better to do. Yeah, because then we'll have 8 here, and then we can take out the 8, and then we're left with 1 minus sine in here. We can take out the square root of 8. Then we're left with s in here. 2 times question is, what do we do now with this? So we got 2, square root of 2. Square root underneath. Like the arithmetic is right. Now to solve this part. This part is, let's see. So the square root of mod of Square root of 1 minus sine theta. Problem is that, like, I mean, we can turn the 1 into like sine squared plus cosine. What would happen if we did have that? So let's see, sine squared theta plus cosine squared theta, then minus sine theta. That wouldn't work, because then that would be squared, these two would be squared, but then, yeah, these two would like cancel each other out. Must be something I'm not thinking of. Say we had this. I mean, that wouldn't really do anything, because then we would have, and then we would have a sign here. That would be, which doesn't make a difference. We're back where we started. Actually, let's take a look at the way this is set up. Maybe I'm missing a step here. Yeah, we did square everything. But I'm missing something. We did write this right. Yeah, this is correct too. So that means it has to be this. The one thing is that now how do we solve this? One minus sine. Well, the square root, like the square root. Okay. What am I missing here? I'm definitely missing something. guess I'm going to have to look at parts of the solution to see. This is number 32. So 32 right here. Yeah, we did that. Oh, it's the same thing. Okay, so we have the same parameters. I mean, at least we know that. Okay, now. I mean, it is polar coordinates, so maybe it's gonna be like. That's what we ended up with here. Use CAS. What's that? Does that mean use calculator? I never heard of that. Oh, they expect you to use a computer for that. No wonder. I mean, is there an intuitive way to actually think about this? Maybe not. Huh. I mean, we got the method right. It's just that we got stuck on, like, actually solving that last part. Maybe I have to look up intuitive way of solving for the square. Unless that involves a squeeze theorem, maybe. I don't know. Like, you guys in the chat, like, is there something I can do to think about this integral, like, intuitively, or is it like, because when I see this, I'm thinking about, oh wait, maybe I'm thinking of the squeeze theorem. Okay, but that was an interesting one. Oh, we got a spiral now. So these problems are pretty interesting because it actually like gets me into yeah, I won't write the solution here because I feel like maybe if we want to tackle it again, we could probably like see like, oh, I was thinking about this and this. Oh, they actually tell you the parameters. Okay, so this one, so A is 0 and B is, and R is this, so the length from pi squared, 2 pi, I should say 2 pi. This is a prime, not squared, right here. Plus 2 theta. Alright. Now 2 pi is theta to the 4th and 4. Oops. Which will lead us... Oh, wait, hold on. Because remember, I have to remember we're kind of differentiating from theta. I mean, integrating by theta, so that might not be in the best interest right now. Unless we have to do integration by parts. So let's just not get into that right now. I'm sure that's the right one, right? Yeah, that's the right one. So this is going to be quite difficult. Theta to the fourth plus 4 theta squared. I mean, I can factor out theta, but the thing of it is that we're integrating by theta, so that might not be the best choice. Is there a technique that I'm not thinking about? I mean, there might be. Just let's see. Because if we take the square theta out, like theta squared, then basically we'll be left with theta that's outside, and then it will be like theta squared plus 4. But it's under the square root, which makes it more difficult to navigate. Now these problems involving like polar curves, or is it parametric curves? Polar curves, yeah. These ones are like a little bit tough. But of course, polar curves are like the more exotic, which makes it more exciting in math. So now I actually got to figure out how I am supposed to implement this. Because I know if we do what I was thinking about before, if we did this, we'd be still left with like many unknowns, and this would come out, but then we have to also integrate it, which is probably going to be not very ideal. Maybe I'll look at this, the way they did the solution, and we'll look at part by part. We won't like scroll down to the solved solution, but we'll go part by part. I think that's like a good way to like look at it. Yeah, that's what we end up with. Okay, so they did the same thing, so I guess we were on the right track here. That's interesting. So they made this U. So if you, oops, this is supposed to be du. Du is equal to theta. Oh. Oh, that's clever. Dang. It was just simple U substitution. Dang. But that's why we practice, because that way we get our math muscles working. I'm pretty sure some of you in the chat were like, no, it's right there. It's obvious. So I guess we're gonna have to do it in the calculator again. So we got 19.8. Dang, I totally missed that trick. Now I'm like, oh my gosh, it was right there. But sometimes you just don't see these things. Can't beat yourself up for that, though. Oh, did I miss something? Maybe I missed a step. Let's see. Now, where did this other half come from? Because I'm pretty sure this is correct. Did I forget something when I integrate? I don't think so. Because I know where this half comes from. It comes from like the crossout, but why is this half here? Because yeah, because this one flips over. Is there another half here? Was there a half that we dealt with before? So I know, yeah, because this half is from here. But why is this here? It looks like everything in the procedure looks similar. I'm just wondering where that half came from. Did they reduce this side? No, I don't think so. I get a feeling they might have made an error on this problem. Let me see if there's like another version that was posted. Because I'm like wondering where they get this other half from. I feel like that shouldn't be there, but then again I'm like wondering like why is it that it just suddenly pops up? Okay. Yeah, I think these problems are giving me the challenge that I probably needed. Let's see, R equals E theta. So it's a spiral. technically it would just be this. I pulled out my calculator and I'm like, wait a minute. Oh no, actually, it probably wouldn't be that. I think it would be like 1, it would be like kind of like -1. So it's like... Because technically it would be like something like this. You would have factored it out. With 7. Just leave it 7.9. I mean 755.9. Oh yeah, because it's supposed to be and. I forgot the and in there. So technically it's not supposed to be this. It's supposed to be this. At least we like got to the finishing point here. So alright, let's try the next one. And I think we'll end stream there. But these problems have been pretty fun, actually. I mean, I got like most of these like not really correct, but at least we're like learning something from each one of these. now we're like into like complicated territory. Let's see, we have. Because I mean, I can only think of grouping, but is there something else we can do? Well, I guess I'll think about this for like next time. This problem is like I think like the further in when you get into problems, like you begin to see like, oh wait, there's like a lot of mess going on, and then you have to figure out how to unravel that mess. But I think we're going to conclude it for today, guys. Thanks for joining me today, guys. If you're watching this on YouTube Live, you know, like drop a comment down below, hit a like on the video if you're watching this like after the live stream, and hit the sub button. Consider dropping a subscribe on YouTube, because I continue to like make math streams, and if you need like someone to basically be like, you know, the background noise for you guys doing your mathematical journey or physics journey or any like, you know, project you're doing on the computer, you know, consider like putting the MathSpellBook live stream in the background so you can actually feel like you're in a productive mood. In addition, I will put links in the description down below if you want to check out my Twitch channel as well as my Discord server. In addition to my my Uncle Talks channel, which is my video game channel where I play like basically video games on my Twitch channel / YouTube. So you can basically check those out. But for those of you who are watching on Twitch, you know, consider dropping a follow if you like math and physics, or you just need like a little study stream to like keep you guys going on your merry way. Because like sometimes a 2-hour session is can take you a long way with whatever projects you're doing, whether it be math, physics, or just any project in general. And yeah, that will be it for today, guys. And we'll be back like next week. So always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys in the next stream. So take care, guys. Bye-bye.